Hi, Jayla. This is a quick little video to just show you the two solutions to the problems you asked me about yesterday. The first one was lesson 10, problem 23, and the problem looked like this. Oh, here, you know what? I already have this copied on my other page. So let me switch to this. Here's what makes this problem tricky. I'll show you. It's this plus sign. That throws a monkey wrench into our usual way of handling these problems. You can't just flip these bases down to the denominator because of this plus sign. It changes the dynamic. You can only do that if there's multiplication. But this plus sign is your trigger that something's wrong. So you can't flip them together. What we have to do instead is create mini fractions in the numerator. Okay, so see what I did? I flipped this one down to a fraction, then I put in the plus sign, then I put this one down in a fraction. That's the new numerator. The denominator, there's no addition, so technically we could flip it up, but because we've already made new fractions in the numerator, let's not get these guys mixed up in that immediately. Let's instead just keep them in the denominator like so. We're gonna figure that out in just a second, okay? So review what we did. In the top, there's a sum, so we cannot just flip them down to the bottom. We have to create their own fractions, and that's all the numerator now. The way we flip them there's nothing tricky about that. And then in the original denominator, rather than muddy the mess that we've already made upstairs, we're just gonna leave it like this. So I just put this down into a little fraction down here. So we've made fractions in our fraction. That means we have a complex fraction. That means that the way that we solve it is the way we're used to solving it, which is to say, let's turn the denominator into a 1. So we'll multiply it by its reciprocal, x to the 6, y squared, right? That cancels and turns all of that into a big fat 1. Beautiful. Now we have to do the same thing to the top. I'm going to put parentheses around this because it is a sum, so it's a binomial. We have to make it protect it in that respect. And then we're going to distribute this outer fraction to both parts. Okay, let's multiply. So we have, won't do any simplifying. X to the 6 over x to the 3rd plus, x to the 6th over x to the 3rd y squared, right? I have to do the top and the bottom. And then the bottom is x to the 6th over y to the 8th. Okay. Let me go get the answer book because I don't have that in front of me. Okay, we're on beautiful track. And now what we can do is to simplify. This one's beautiful, this is fine. This one we can simplify because we can see that we have x's in the bottom and the top. So we're gonna subtract 3, right? Because the quotient rule says take the top exponent, subtract the bottom. That takes care of that. So now we have x to the 3rd over y squared plus x to the 6th over y to the 8th. And then, that's an exponent, sorry, it looks messy. And then our final step is we have to multiply this side in order to make the denominators match. So the least common multiple for the denominator is y to the 8th. So we'll have to multiply this one by y to the 6th over y to the 6th. And when we add these two, we'll get the 8 and they will be able to match. And so our final answer, I'm going to go this way, is x to the third, y to the sixth, plus x to the sixth, that's a messy x, plus x to the sixth, all over y to the eighth. And let me just double check and make sure that's right. X to the third, y to the sixth, plus x to the sixth over y to the eighth. Yes, final answer. Vivian and Laura asked me about this one too, and it's right there that the drama comes in with that plus sign. Okay, that's 1021, the other, or 1023 rather. The other problem you asked me about was 1127, lesson 11, problem 27. And that problem looks like this. Okay, there's a numerator and a denominator. We have to simplify each one and then combine them. So let me start with the numerator. I'm not going to copy the whole problem down at once. Okay, the numerator is x okay. This is just the numerator, remember. Okay, so the problem here, the messy situation, is that we've got fractional exponents, but then we've got a square root sign. So we remember that we can rewrite a radical sign into fractional exponents by taking whatever root is. If it's invisible, it's a 2, and making that the denominator of a fraction. This is already x to the third, so we'll multiply like that. So this becomes, this part stays the same, x 3a plus 2, and then it becomes x to the 3/2, which is the radical sign turning into a 1/2, and then times that 3, which is what I showed you right there. And then this is still raised to the 2a power. So first we converted the radical sign to a fraction. Now we're going to use the power rule to remove the parentheses. So again, x to the 3a plus 2, that's fine. And then we have x to the, and it'll be 2a over 1 times 3 over 2. The 2's will cancel, so it becomes x to the 3a. Now we can use the product rule to simplify one more time, and that will become x to the 6a plus 2. Okay, that is the simplified version of our numerator. Let's go to the denominator now. And this is the way I prefer to lay these out. I don't like to just keep writing the top and bottom every single time. I'd rather focus on just the top and then just the bottom and go from there. The denominator is y to the 2a minus 4 with another radical sign that we're going to have to deal with. This time, the number inside is not being raised to any power, so that's a little bit more straightforward. It is x to the 1/2 times 2a plus 1. Remember, this is over 1 when we go to multiply. The y stays the same. And this becomes, let's see, it's going to be x. When I multiply 1/2 times 2a, the 2's will cancel because we're distributing, right? 1/2 times 2a, the 2's cancel, and I just get a. And then 1/2 times 1 is just plus 1/2. Okay, so this is my denominator simplified. Now we're going to put them together and see if there's anything more we can simplify. So I have x to the 6a plus 2 over y to the 2a minus 4, and then x to the a plus 1/2. Okay, we know that the quotient rule tells us that we subtract if the bases match, we subtract what's in the denominator. Okay, so that's going to be, I'm going to make this list over here. For x, it's going to be 6a plus 2 minus a plus 1/2. I put the parentheses around here to remind me that this whole thing gets subtracted, not just minus a and then plus 1/2. It's got to be minus a minus 1/2. So I'll rewrite it that way. 6a plus 2 minus a minus 1/2. Starting to run out of space, so I'm getting a little bit smaller. And now we can simplify this. It's x to the 5a plus 3 over 2. Right? Because 2 minus 1/2 would give us 3 over 2. Okay, that looks good. Now so we've combined the x in the numerator and the x in the denominator. Here's the new combined version. The y's, does John tell us to write this all in the numerator? The answer, he presents everything in the numerator. So that's what we're doing. The y's will just reverse the signs on both parts of the exponent and it'll be fine. So here's the final answer. It is x to the 5a plus 3 over 2 times y to the minus 2a plus 4. I reversed both of those signs as I bring them up. If it helps, you can think of there being a y to the 0 power up there. Remember, anything raised to the 0 power is a 1. So if it helps us, we can always add this concept, and then our y exponents would be 0 minus 2a plus 4, which is what we have here. And then that gives us the answer that I just did in my head. So this is another way to conceptualize what we're doing here. Okay, final answer. I like it like this, but what John does is he changes this to, instead of 5a, he makes it 10a over 2, so that he can bump those two fractions together and write it like this. And then he just changes the order on this. He writes it as 4 minus 2a. Same difference. I personally like this one just as much, if not better than this one, but either two of these are happy and adorable. All right, that was a hard problem. Good questions. Let me know if you're still confused. Thanks, Jayla. Bye.